and I've been working at COMSOL for a little over 9 years, and I have spent the last 2 of them in Sweden as a part of the global support team. Understanding and managing uncertainty is crucial for achieving more accurate and reliable simulations in high-frequency devices. Today, we'll explore how incorporating uncertainty into the design process allows for better optimization, risk assessment, and overall performance prediction. This knowledge is essential for improving the robustness of microwave and millimeter wave technologies. Just a heads up, I won't delve into advanced theoretical aspects of uncertainty quantification and just state it's 101 and then focus on the particular antenna example, trying to make it as practical as possible. Apparently, running an uncertainty quantification model from scratch takes a decent time beyond the 40+ minutes we have. Therefore, I have the main considerations and results covered within the slides. Nevertheless, my plan is to go over them and then open the software and briefly show the main stages, together with the user-friendly GUI design and the high level of automation offered. Feel free to ask questions through the chat window. I'll try to keep track of them and comment on everything that is within my competence during the Q&A session at the end of the webinar. We experience uncertainty in every aspect of life, from the kitchen to the manufacturing floor. Let's start with something simple. For instance, everyone in Sweden has their favorite food recipe. Even when following the same steps, slight variations in ingredient quality, temperature, or cooking time can lead to different results. This is uncertainty in action. Now think about sports, hitting the best golf shot or the perfect tennis stroke. Even the most skilled athletes deal with uncertainty. Factors like wind speed, ball spin, and slight variations in muscle movement can all influence the outcome, making consistency a challenge. The same applies to vehicle maneuvers such as simply driving. Whether it's making a sharp turn or an emergency stop, road conditions, tire grip, and reaction time introduce uncertainty. That's why driver-assisted systems and simulation test countless scenarios to improve safety. In science, experimental studies are full of uncertainties. Measurements and environmental conditions introduce variability, which researchers must account for to draw reliable conclusions. And in manufacturing processes, even the most precisely controlled systems have variations. Material properties, machine wear, and environmental factors contribute to slight deviations in product quality. This is why uncertainty quantification is so valuable. It helps us analyze, predict, and minimize variability, leading to more robust designs and reliable outcomes. Uncertainty is everywhere, but with the right tools and analysis, we can manage and even leverage it to our advantage. The uncertainty quantification module, which is a multi-purpose add-on to the COMSOL Multiphysics software platform, belongs to a list of such tools. In the world of simulations and real-world processes, we often distinguish between determinism and uncertainty. Deterministic simulations operate under the assumption that all input data are fixed, often to 16 decimal digits in a computer. This means that given the same inputs, the model will always produce the same output with controlled accuracy. These simulations help engineers design and optimize systems with the high precision. A typical finite element model is a good example of deterministic simulation. However, uncertain reality tells a different story. In practical applications, whether in a fabrication, prototyping, testing, or manufacturing, uncertainty is everywhere. No two manufacturing runs produce identical parts. No two measurements are free of noise, and external conditions introduce variability. This contrast highlights why uncertainty quantification is crucial. By integrating uncertainty into our numerical models, we move beyond the idealized world of determinism and embrace reality's complexity, leading to more robust designs, better decision-making, and improved reliability. So while deterministic simulation give us a controlled framework, uncertainty quantification ensures that our designs hold up under real-world conditions. Uncertainty quantification often relies on Monte Carlo simulations, where input parameters are randomized based on probability distributions. The model is often evaluated multiple times for different inputs, allowing us to estimate statistical properties of the selected outputs. We usually call the latter as quantities of interest, or just QOI. The challenge is that Monte Carlo methods require an extremely high number of simulations, which can be computationally expensive, especially for complex physics-based models. To make this process more efficient, we use surrogate models in COMSOL. These are simplified data-driven approximations of the full physics model. Instead of running thousands of simulations directly, we train a surrogate model using a limited number of full model evaluations. Once trained, this surrogate model can be used for Monte Carlo-based uncertainty quantification analysis at a fraction of the computational cost. By reducing the number of expensive simulations, surrogate models accelerate uncertainty quantification, making it practical and scalable. They allow us to gain insights into variability and design robustness without overwhelming computational resources. Let's move on to radio frequency industry. Designing high-frequency devices demands careful consideration of how material properties and manufacturing tolerances impact performance metrics such as resonance frequency, return or insertion loss, gain, radiation efficiency, and etc. Even minor variation can lead to significant deviations from expected performance. This is where we can leverage uncertainty quantification tools. Microstrip patch antennas, common in wireless, radar, and satellite systems, are particularly sensitive to such uncertainties. Integrating uncertainty quantification into simulation workflows helps assess how changes in substrate thickness, material permittivity, and fabrication tolerances affect key metrics like resonance frequency, gain, efficiency, ultimately leading to more robust and reliable antenna designs. And a relevant example of this approach can be found in COMSOL's application library as of version 6.3, and a detailed discussion was also featured in the March 2025 issue of Microwave Journal prepared by Ji-Yoon Moon. This webinar has been built on them. Let's take a look at the direct microstrip patch antenna simulation model first. It is configured with several key physics features. The materials include air and dielectric substrate, which can influence the antenna's resonance and radiation characteristics. The study is conducted in the frequency domain at 1.575 GHz, which is a common operating frequency for GPS applications. The model uses perfectly electric conductor to represent a metallic patch and ground plane that is lossless or can be considered as lossless and thus neglectable. We also use lamp port for excitation. We use far field calculation feature to analyze radiation patterns, and perfectly matched layers to absorb outgoing waves and prevent reflections. By capturing these essential physics aspects, the model provides a basic foundation for uncertainty quantification studies to examine how variations in material properties and fabrication tolerances impact antenna performance. When designing microstrip patch antennas, simulations provide an idealized performance estimate. Suppose we fabricate a batch of 100 microstrip patch antennas, all designed based on a simulation model that predicts an S11 parameter of minus 20 dBs at the center frequency. And just to fix somewhere on my PC, it takes about 10 seconds to run a 1-point frequency domain analysis. However, in real-world manufacturing, variations in material properties, etching precision, and substrate tolerances introduce uncertainty. The key question here is how many antennas will meet the design target of S11 parameter below or better minus 10 dBs after fabrication. As you may know, the threshold of minus 10 dBs is conventionally used, and when it's lower than minus 10 dBs, the reflection due to the impedance mismatch is considered as acceptable. This challenge highlights the gap between simulation and actual performance. By incorporating uncertainty quantification, we can predict the expected yield and assess the impact of fabrication variations, ensuring more reliable designs in production. Time to select our input uncertainty quantification parameters. In real-world fabrication, the variations in substrate thickness and dielectric constant can significantly impact antenna performance. These variations are typically provided by manufacturers in datasheets and must be accounted for in the design process. One more factor to consider is the patch length, which can vary due to the selected fabrication method and its precision. For all input parameters, we are going to consider a normal distribution based on the standard deviation and truncate the right and leftmost tails to keep our analysis rather simple. The substrate thickness, D, can vary within about plus minus 7% based on the manufacturer's datasheet. If the standard deviation, sigma, for the thickness is 3.5% of the nominal thickness, and then the range specified by D plus minus to multiply sigma will cover approximately 95.5% of the variations. The tolerance for the patch length, L_patch, is initially based on a scenario using a milling machine with a loosely anchored circuit board. This results in an undesired tolerance of 2 sigma or 0.52 millimeters, where sigma is 0.5% of a nominal patch length. After computing the probability of conditions for this scenario, an error reliability analysis is performed assuming non-high precision PCB fabrication with an etching tolerance of 0.13 millimeters. So we set the standard deviation for that case 4 times smaller. According to a manufacturer's datasheet, the dielectric constant dk is given as 3.38 plus minus 0.05. For strict range coverage such as 99.73%, so almost 100%, the dielectric constant is selected to vary within dk plus minus 3 multiply sigma, where sigma is again 0.5% of nominal value for dk, while plus minus 3 sigma gives stricter coverage. Plus minus 2 sigma is often sufficient for most applications like manufacturing and quality control. Here, both are shown just to illustrate different options. Initially, uncertainty quantification involves many input parameters, but not all of them have a significant impact on the quantities of interest. The Morris one-at-a-time method is a screening technique used to identify the most influential input parameters before conducting more detailed uncertainty quantification analysis. The MOAT workflow consists of input selection and design of experiments, followed by model evaluation through multiply direct simulations, and at the top, we perform plot analysis to visualize parameter influence. MOAT mean measures the average effect of each input parameter on the quantity of interest. MOAT standard deviation indicates the variability or uncertainty in the effect of each input parameter, highlighting interactions with other parameters or nonlinear effects. For a microstrip patch antenna, the MOAT method helps us filter out less important parameters, making the uncertainty analysis more efficient by focusing computational efforts where they matter most. In this example, we exclude the thickness of the substrate D. Here you can see that both metrics are way smaller than metrics for the two other parameters. And just for reference, on my PC, it takes about 2 minutes to go through 16 data points. To meet up high tolerance, one might want to increase the number of numerical experiments. While screening is used to qualitatively rank the significance of input parameters, sensitivity analysis using the COMSOL method quantifies the contribution of each input parameter to the variability in the model output. This method enables you to identify which parameters have the most significant impact, both individually, measured by the first-order COMSOL index, and through interactions with other parameters, as indicated through the total index. By analyzing these indices, we can refine manufacturing tolerances and optimize designs to enhance performance while minimizing variability. Sensitivity analysis ensures that engineering decisions are backed by a quantitative understanding of parameter influence, leading to more robust and predictable system behavior. Sensitivity analysis is the point at which we first encountered the surrogate model in today's session. To accelerate the sensitivity analysis, this study type uses an adaptive polynomial chaos expansion surrogate model. Please note that the creation of the surrogate model is automated, ensuring that the model is solved a minimal number of times. During the computation, the input parameter space is sampled using a Lathin hypercode sampling-based design of experiments method. The PCE surrogate model is adaptively improved during this process until either the tolerance or the maximum number of sample points is reached. What do they get here? In this case, the first order and total indices, this is first order and this is the total indices for the first parameter, and this is the first order and total indices for the second parameter. So we can see that they are not equal within the computed accuracy for all parameters, suggesting significant interaction between parameters. The COMSOL plot reveals that the length of the patch is the most sensitive parameter, which aligns with the findings from the previous screening analysis. My PC runs this study for approximately 5 minutes, covering 40 input points in total. Again, the better tolerance you want, the more sample points and time you should reallocate. To analyze how parameter variations influence the distribution of S11 parameter, we use kernel density estimation. It estimates how probability density estimates the probability density function of S11, providing a continuous representation of its likelihood across different values. This is to be done via the uncertainty propagation study. To accelerate this uncertainty propagation analysis, this study type also uses a surrogate model, specifically an adaptive Gaussian process surrogate model. By incorporating KDE into uncertainty quantification, we can better predict how real-world variations affect performance and refine designs for improved reliability. Here, we build up from the previous surrogate model and can almost immediately get the result. Hence, we opt for the analyze-only action. Result-wise, we can see a mean value of about minus 12 dBs and a pretty huge standard deviation, which means we can easily fall out of the predefined range for the quantity of interest. The next logical step is to quantify the probability of meeting design targets such as S11 less or better than minus 10 dBs for a microstrip patch antenna via the so-called reliability analysis. Let me remind you again, the threshold of minus 10 dBs is conventionally used in the industry, and when it's lower than minus 10 dBs, the reflection due to the impedance mismatch is considered as acceptable. The reliability analysis will focus on the model evaluations in the critical regions necessary to increase the accuracy of the surrogate model and thereby the requested probability estimate. Like surrogate-based sensitivity analysis and uncertainty propagation, reliability analysis is also built using a surrogate model. It uses an efficient global reliability analysis method, which is based on adaptive Gaussian process surrogate model again. By analyzing these probabilities, engineers can make data-driven decisions to refine fabrication methods, adjust tolerances, and improve overall yield. Reliability analysis plays a critical role in bridging the gap between simulation and real-world performance, ensuring better product consistency and manufacturing efficiency. We test here two cases with a notable difference in the standard deviation for the patch length that mimics two fabrication methods. Myelin yields 55% reliability, meaning nearly half of the fabricated antennas, 45 out of 100, may not meet the target. PCB etching yields 86% reliability, demonstrating a more precise and consistent process with 86 decent antennas out of 100. Each study lasts about 3 minutes on my workstation. So, time to open COMSOL Multiphysics and get some real-life experience on how apply uncertainty quantification to a microstrip patch antenna, considering variation in patch length, dielectric constant, and substrate thickness. I already had COMSOL session opened with a microstrip and patch antenna model. This model, almost a replica of our basic tutorial from the RF module. I've updated it a bit just to introduce an extra parameterization and some polishing in the results session. So let me briefly guide you through the model. So here we have our substrate with the height set as D. That's our first input parameter. Next, we'll have another block representing the patch. Essentially, in the model itself, we're going to use only its surface, but again, here we use our second input parameter, that is L_patch. Okay, here's the full model with the extra layer of perfectly matched layers. And while assigning material properties, we specify our user-defined properties for the substrate with our third parameter dk that represents relative permittivity of the substrate. Physics-wise, we use our standard and most popular electromagnetic wave frequency domain interface. We specify all metallic parts as perfect electric conductors. We use the lump port to specify connection to a coaxial cable. And additionally, we choose the far-field domain feature to do some cool post-processing and to get some far-field patterns. So, and yeah, to mimic open boundaries, we rely on the perfectly matched layer. Okay. As for the study, here we use the standard frequency domain study step with the single frequency specified. Again, you can see that the model takes about 9 seconds to run, and we use our standard physics-controlled mesh. And results-wise, we can get a lot of cool visualization of electric fields, far-field patterns, and of course, our key metric here, which we're going to use as quantity of interest. That's an S11 parameter that's specified in the table, and we can see that it's slightly below -20 dBs. As an extra study step here, we have frequency sweep, so we can check the frequency spectrum of our antenna design and confirm that it's has a pretty narrow resonance. So it's pretty easy to mess up something and fall out of the target value of about -10 dBs. So let's investigate it. So our interface offers a pretty simple and straightforward way to add an uncertainty quantification analysis. What we need is to call the pop-up menu from the basic study and add an uncertainty quantification study using study reference. So here we see the study reference to the basic study, and on top of that, the uncertainty quantification node that looks and acts almost like an optimization study step, which I believe kind of more familiar for all of us. So here we start with the default basic screening study type and opt for compute and analyze action. Our next step is to specify quantities of interest, and here we use the expression for our key metrics. And next we can specify our three input parameters, and give me a second. Okay, so the first input parameter will be substrate thickness. We can choose within any parameter specified under the global parameters node. So we choose normal distribution with the mean value equal to the nominal value, and the standard deviation here, it's 3.5% of the nominal value. And next we can also choose for some predefined option for the lower bound and the upper bound, or just type them manually, and that's what we're going to do here. So I'll specify the lower bound as d minus 2 multiply sigma, and the upper bound as d plus 2 multiply sigma. Okay, let's add the second parameter, and it will be the length per page. So again, we opt for the normal distribution type. We use the nominal value as a mean value and specify standard deviation. Initially, it will be 0.5%. And again, we should spend some time to specify lower bound and upper bound. I'll patch minus 2 multiply sigma, and I'll patch plus 2 multiply sigma. Okay, and the third parameter, it will be the dielectric constant of a substrate, and all the procedure is the same. Here we specify the mean value of decay, standard deviation of, again, 0.5% of decay, and lower and upper bounds. Here we choose plus minus 3 sigma to cover almost the entire range of variations for this parameter. Okay, guess we're done. So in total, we can see 16 input points that is obtained, like 3 parameters multiplied by 5, and I guess there's some extra rounding to an even number. So we can run our simulation. as I said, it should take about 2 minutes or slightly more, depending on the software, on the hardware, of course. Yeah, and let's just cancel that simulation and check the model stage after we run that study that I pre-saved while preparing for that webinar. So here you can see that after we run our first screening analysis, we get a cool plot with standard deviation and mean value, and can analyze and can notice that the thickness influence is way smaller than influence of 2 other parameters. You can see that that plot is grouped with the correct naming. I've just added an extra tag. And under the tables node, you can see the table that was written during analysis. So again, you can use these numbers. And also you can check that we ran 16 direct calculations for 16 combination of input parameters. Okay, if we want to continue with the next uncertainty quantification study, again, we have a cool shortcut. So you can click on the predefined study and select option to add new uncertainty quantification study for null sensitivity analysis. And it comes with quantities of interest and input parameters taken from the previous step. So we can save a lot of time. And here we can remove or get rid of the first parameter since it's less influential than other parameters. So let's delete that. And again, we can run, and it should take about 5 minutes. Instead of that, let me open another stage of that model after we ran that second uncertainty quantification analysis. And you can see that here in the first surrogate model used, and we can check the results in form of Sobol indices. Here you go. And again, some extra data available under the tables node. And we can also see the surrogate model added in the global definitions node. Technically, you can use it as a function for some extra analysis. And also you can check here some extra log information. Okay, let me demonstrate another study type. And since it's going to be pretty fast, I can perform the full analysis live. So we can add another study for uncertainty propagation. And since we are going to build on the previous surrogate model, we can just select analyze only option, and it should take about a second or so to get a result in form of KD plot. And apart from that plot, we can also check some important digits, important values here. So the mean value is about minus 11.6 dBs, and we have a pretty huge standard deviation. Okay, and the icing on the cake, the final configuration of that model with 2 extra reliability analysis study steps, it returns actually just 2 important numbers. one, that's the probability according to the specified target value of -10 dBs. And we repeated the same study for the tightened standard deviation for the patch length, and it gives us more precise result with about 86% reliability. As an extra visualization, we can check so-called response surfaces, which depicts both input parameters and output quantity of interest in such a surface plot, and we can add an extra height expression to make it a bit more informative. Okay, and let me return to my slides. There were a series of analyses, and you might have felt overwhelmed or at least overloaded with new information. So let me summarize it. Uncertainty quantification is essential for understanding how variations in input parameters impact performance. This process includes several key steps. Screening uses Morris sensitivity metrics to rank input parameters by their influence. For the patch antenna, it identified the patch length and the dielectric constant as primary influencers. Sensitivity analysis quantifies the fractional impact of each parameter on the quantity of interest using first order and total Sobol indices, direct and interaction effects respectively. It confirmed screening results and showed significant interaction between parameters. Uncertainty propagation evaluates variability of the quantity of interest and computed its probability density function to characterize uncertainty and highlight the distribution around the S11 threshold. We can see a pretty big standard deviation, which says that we can easily fall out of the predefined range with the specified tolerances. Finally, reliability analysis determines the probability of meeting performance criteria to assess design robustness. It quantifies success rates, guiding process refinement. In the case of PCB etching, we get about 86% reliability. By systematically applying these uncertainty quantification techniques, engineers can optimize designs, refine tolerances, and improve the reliability of real-world manufacturing processes. On the slide, a motivated participant can find a little Easter egg, one more type of uncertainty quantification study available in COMSOL since version 6.2 that I have not mentioned tonight. Inverse uncertainty quantification can be used when some of the input parameters have unknown probability distributions, known as calibration parameters. Using inverse uncertainty quantification, experimental data can be propagated backward to gain insight into the statistical properties of these calibration parameters. In order to apply inverse uncertainty quantification, a prior probability distribution is required for each calibration parameter before the analysis can be conducted. And this is all I wanted to show you today, and time for the Q&A session.